Hello everyone, welcome to section 1 of this second part of PHAS0006. So in this section we are going to talk about real gases. So we'll start off with the ideal gas equation that you've already learned in the first half of this module. And we'll look at what the limitations of this equation are and how we can modify it in order to better describe the properties of real gases. And in doing so, we will learn a little bit about why gases condense into liquids and solids. So this second part of PHAS0006 will be divided into 4 sections in total. And for each of the sections we'll have, sort of a section title slide like this. And I just wanted to mention a couple of things about the title slide. The first and probably most important is that just here you can see some recommended sections of the textbooks. So the notes are designed to contain all of the information that you need to study the module. But nevertheless, I always recommend to sort of supplement your learning by doing some reading from these recommended texts. So please look at this title slide for each of the 4 sections and you'll see the recommended sort of chapters or chapter sections from the textbooks. And typically I've used these chapters and sections in writing the notes in the first place. And the other point is that down here there's a date. This is the sort of latest date that the document was updated. So if we happen to find any typos or other errors in the notes, then I'll update them, and this date in the bottom corner then allows you to know which version of the notes that you are working with. Okay, so the ideal gas equation that you've already learned is this one here. PV is equal to nRT. So P is the pressure of the gas, V is the volume that the gas is occupying, N is the number of moles of the gas, in other words, the number of particles, either atoms or molecules that make up the gas, the particular sample of gas that we have. R is the gas constant, and T is the temperature. And as you've seen in the first half of this module, this equation works very well under a range of conditions, and we can use this equation to examine various problems as you've done in the first half of the module. But it doesn't work well under all conditions, and particularly it doesn't work well at very high pressures or very low temperatures. And the other thing is that it predicts then that a gas will remain a gas at all values of pressure and temperature, and that's something that you know from your everyday experience is not the case, right? So you know that eventually, if you take a gas and you lower the temperature, it'll become a liquid, and if you lower the temperature further, it'll become a solid, right? So the most common example that we encounter is steam converting to water, then converting to ice. And maybe you don't have so much direct experience with variations in pressure, but the same is true as we vary the pressure. Okay, so this equation works well. The ideal gas equation works well at low pressures. That's right. At low pressures and high temperatures. Yeah. But it doesn't accurately describe the properties of real gases at high pressures and low temperatures. Okay, so the other thing I wanted to briefly mention here is molar volume, or we might also talk about a specific volume. So the molar volume is simply the volume that would be occupied by 1 mole of our gas, right? So if we had, say, 3 moles of a gas, then we can measure the volume of those 3 moles of the gas. We divide that by 3, and that gives us the volume that 1 mole occupies. And then with the molar volume, then we can re-express the ideal gas equation as Pvm, where Vm is now our molar volume is equal to RT. And this is simply because for 1 mole of gas, then N is equal to 1. Okay, but this is all very much revision from the first part of the notes, as is this graph. So this is now a typical PVT surface for an ideal gas. And you can see this is just a nice monatomic function in temperature, volume, and pressure. Right? So as we've said, this is accurate at high temperature, low pressure, but not at not under all conditions. So it's not accurate for real gases at low temperatures and low temperatures and high pressures. And it is very useful. The ideal gas equation is very useful. You can use it to do problems as you've done in the first part of the notes. Okay, and the ideal gas equation doesn't explain the conversion of gases, the phase change of gases, into liquids and solids. And so you can compare this this PVT surface to the one that we had on the title slide, and anyway, we'll talk a little bit more about that later. Okay, so the reason that the ideal gas equation is not working well under all conditions is because of the assumptions that we make in deriving the ideal gas equation. So if you remember, these were the assumptions that we made. So the first was that the atoms or molecules of the gas behave as ideal point masses, okay, but each particle occupies no volume, right? So they're infinitesimally small particles. And that's obviously not realistic. We know that real atoms and molecules occupy some amount of physical space. Okay, so a very small amount of physical space, but we have a very large number of molecules or atoms in our gas. And then the second assumption here is that the atoms or molecules of the gas do not interact, right, except for these sort of instantaneous collisions when they collide with one another. Okay, and so, but in fact, there are some attractive forces between the gas particles, and these are typically quite short-ranged interactions, but they exist, and they change the properties of the gas. Okay, and so both of those first two assumptions we will talk about a little more. The third assumption here is that the collisions are elastic. Okay, we're not going to do anything with that third assumption. Okay, so here now I've got some slides to illustrate these ideas, right? So let's first look at the idea that gas particles have a finite volume. So what I've done is I've just made these two sort of simple diagrams kind of representing our volume of gas just in a two-dimensional drawing. Okay, so in each of these boxes we have 25 particles. Obviously I can't draw real infinitesimal particles, but the idea of the plot on the left is that the gas particle, these 25 dots you see in there, these are infinitesimally small particles in our ideal gas model. On the right hand side, I've drawn again 25 particles, but now I've made them, made the dots themselves larger, and that's supposed to sort of visually illustrate the idea that the gas particles have a finite amount of volume, right? So you can see that these particles are actually taking up some of the volume in this container, right? So if I were to try and draw, let's just quickly do this one. So if I just sort of sketch there, that's about 20. If I didn't quite count, but that's about 20. That's about 25 of these particles. If I were to push all of these particles into one corner, they're going to take up, like quite a reasonable volume in this container. And so what that means is that the amount of volume that's left for the particles to move in, is just this kind of crosshatched region that's left over. So you can see that the effective volume that the particles are moving in is smaller because the fact that the particles themselves have a finite size. And so that equates to, there's a smaller volume which would equate to an increase in the pressure. Right? And so underneath the two diagrams, I've got these equations. So this is our ideal gas equation, so rearranged, so its pressure is equal to nRT over V. And then under the plot on the right, I'm foreshadowing this equation. This is the van der Waals gas equation. And we will talk about this in more detail later, but so I'm just sort of putting it on here for the purposes of illustration. And so you can see here now we've replaced the volume V by now the volume V minus NB, right? So B here is the volume of the individual particles, and then so NB would be kind of the volume that's taken up by all of the N particles. So you can see that we've the denominator of this equation here, which was just the volume in the case of the ideal gas equation, has now been reduced, right? So the volume V has been reduced by this amount, N, which is the number of our particles, times B. Well, in fact, N will be the number of moles and B will be the volume per mole. And then we talked about the fact that these effects become more pronounced as we go to higher pressures and lower temperatures, right? So that's what I've tried to illustrate on this slide. I've now increased, on the previous slide we had 25 particles in each of the two boxes, right? And on this slide now we have 200 particles in each of the boxes. And this just highlights the fact that this sort of the reduction in the volume, or the increase, with the corresponding increase in pressure for real particles is going to increase, sort of scale as the pressure for higher pressures. This effect is more pronounced, right? So that's kind of trying to illustrate this first assumption here, that the atoms or molecules of the gas behave as ideal point masses, right? Where real gases, they don't. Oops. Okay, and now on this slide, I'm trying to illustrate the concept of the attractive interactions, right? So there tends to be some attractive interaction between the particles in our gas, and again, we'll talk about this in more detail later in the module, but so just for the moment, we're just saying that there is an attractive force that exists between our gas particles. And the attraction tends to be reasonably short-ranged. So what I've done on these diagrams is drawn now a little red arrow, to indicate where a particle is feeling an attraction to another particle. Yeah, and so for example, if we look at these two here, they're quite close together, and so they're feeling an attractive force, and so I've drawn the two red arrows to indicate that they're feeling this attractive force together. But if you see these two particles that are separated by a slightly larger distance, then they're not feeling any interaction. Okay, but nevertheless, we can see even with 25 particles, we can see there's an appreciable number of these particles that are feeling this attractive force, and that's going to change the properties of the gas in some way. Again, as we go to higher pressures, so here on the right, I've now drawn the same diagram, but with 200 particles, and you can see now basically every particle in our box is feeling some kind of attraction to another particle, one or more particles in the box. So you can see again that this effect is going to become more pronounced as we increase the pressure. Also, these diagrams are just supposed to be a sort of instantaneous snapshot of the positions of the particles. Of course, we know that the particles have a kinetic energy, and they're all sort of moving about inside the box. I'm not trying to draw any motion on the diagrams. But you can imagine as we lower the temperature, then the particles are moving more slowly, and so they're going to spend more time close to each other, and so again, the attractive forces are going to become more important. The equation at the bottom then again is this is now the second term that's relevant to the van der Waals gas equation. So we're adding on this minus a n over v squared term, which arises because of these attractive interactions. But again, we'll talk more about the van der Waals gas equation later in the notes. Okay, so that then was sort of addressing this second assumption of our that we made in deriving the ideal gas equation. So then, just sort of summarize this illustration. Then what we have seen is that the fact that the particles in the gas have a finite size makes it harder to compress the gas. Okay, because the the gas molecules themselves occupy a finite size, and so it's as if the particles are moving in a smaller volume, and there's less free space for them to move to move around in. And the ultimate limit is, of course, when the pressure becomes so high that all the molecules are sort of pushing up against one another, and this is, of course, when we're getting into the liquid and the solid regimes. Okay, and then sort of conversely to that, we've also said that the gas particles have they feel an attractive interaction to each other when they become close, right? So there's sort of this force that's kind of pulling the molecules together, or the atoms or molecules of the gas together when they get close, right? And you can kind of see that this is going to make it easier to compress the gas, right? So there are these sort of two competing factors. The finite size of the particles is making it harder to compress the gas, and the attractive interaction is going to make it sort of easier to compress the gas. Okay, and we'll pick up with that topic in the next video.